let's talk through some of the key characteristics of graphing exponential functions. So we want to add exponential functions to our list of basic functions. So something we'll talk about are graph transformations and how they show up within exponential functions. But first, let's just focus on looking at kind of the two types of exponential functions. So what we're going to do is we're going to graph 2 to the power of x and 1/2 to the power of x. So what we could do is make a table of values. So x and y, and let's go, well, let's start at 0 and then go up from there, and then we'll talk about the reverse. So if we plug in 0, any exponent of 0 will give you 1. And notice that with this function, we're taking out the initial value. We don't see a showing up there. And it's because that value of a, if we have something multiplying on the outside of our function, that's our vertical stretch. So it does give you that initial value. It's just that we assume we start at 1. And then if you have a value out front, that'll stretch you to wherever you need to go based on that number. Okay, 2 to the power of 1 is 2. 2 to the power of 2 is 4. And then 2 cubed is 8. So let's go ahead and graph some of those pieces. So 0, 1, 1, 2, and 2, 4, and 3, 8. Now, on the negative side of things, -1, -2. So 2 to the -1 power, so that flips our fraction. So that'd be a 1/2. So that'll give us a 1/2. And the -2, just so we get a refresher of that, if we have 2 to the -2, that's like 1/2 squared, which is 1/4. So we're going to get a 1/4 out of that. So with that, we'll have a 1/2 and a 1/4. And then you can imagine 1/8, 1/16, 1/32. What's going to happen is it's going to get very close to 0. We're going to have teeny tiny fractions, but it's never going to actually equal 0. So what this does is it creates a horizontal asymptote. So we're going to have an asymptote at y equals 0 here, where our graph is going to get infinitely close to it, but never touch. So our graph is going to look like this. Yeah, I can draw that a little better. Sorry, it's nice to have these sensitive pens on these screens, but sometimes to make it very clear. Okay, there we go. So it's a smooth curve, and this is going off to infinity. So something we get out of this graph is that horizontal asymptote is key. At y equals 0. And something we should notice is that as we read this function left to right, it's increasing. So this graph is showing us exponential growth. So as x is increasing by 1, we're doubling our function. So we're 1/2, double it to 1, double to 2, double to 4, double to 8. Alright, over here with f of x equals 1/2, so let's look at what happens when we plug in. We'll go -2, -1, 0, 1, 2, 3. So at -2, it'll flip it, so we'll actually have 2 in there, and then squared. So at -2, we'll be up at 4. 1/2 to the -1 flips our fraction, so that would just be 2. With the 0, we get a 1 out. With an exponent of 1, we have 1/2. Squared would be a 4th. Cubed would be an 8th. So for our graph, at -2, we'll be up at 4, and then 2, 1, 1/2, 4th, 8th, and closer to 0 on that right-hand side. And if I had done -3, that would have been up at 8. So with this function, we have that same asymptote at y equals 0. So that stays true. And then this is the idea of exponential decay. So this also has that asymptote, and then this is exponential decay. So exponential growth versus decay is coming from our value for b. It'll be exponential growth when that value for b is more than 1, and it will be exponential decay when it's a fraction between 0 and 1. Alright, so what we're going to do is look at transformations. So, as a refresher with transformations, what we could have is whatever our function is, was it minus h or plus h? And let's see, close our function. There we go. Alright, so function transformations. We had these pieces. Multiplying on the outside of the function gave us our vertical stretch compression. Multiplying inside the function was horizontal stretch compression. Adding to x inside the function was a horizontal shift left and right. And adding on the outside of the function, adding or subtracting, was our vertical shift up and down. So let's just go over to Desmos for a moment and just kind of play around with this. We're going to look at some specific examples, but let's say our function is 2 to the power of x. So that piece is our exponential function piece, so that's our f of x. So if I add values on the outside, so if I go plus 2, we can see that moved the graph up 2 units. So I can see my horizontal asymptote is now up here at positive 2, and then everything just moved upwards. If I subtracted, so like minus 3, now I could see my horizontal asymptote's down at negative 3, and my function didn't really change shape. So adding or subtracting on the outside of the exponential piece, so outside of your growth factor with the exponent, is going to move the function up and down. We could multiply on the outside, which we've actually seen already. So if I go 3 times through the x, now we can see that initial value of 3 coming through, and what happened was this vertical stretch. So it started at 1, but then if you multiply 1 by 3, it takes you up to 3. Where we had the point 1, 2 before, now we have the point, what would it be, 6. So 1, 6. So all of those y coordinates got multiplied by 3, and that gave us the vertical stretch. If we wanted to see the vertical compression by a half, we can see, okay, there's our initial value of a half. Where we had 1, 2 before, now we can see it's 1, 1. So all of those vertical distances compressed by a half. So that's how you can see the vertical changes coming through, and again, and we could reflect it by multiplying by a negative out front. That reflects it over the x-axis. So those vertical changes are all happening on the outside of the function. To see horizontal changes, that's going to happen inside the function, which the inside of the function is all about that exponent. So if I wanted to reflect over the y-axis, so changing it horizontally, you'd see negative x coming through there, which actually, that's the same function as 1/2 to the x, which I'll show that in an example that we actually look at. I'll describe that more. If I wanted to shift it left or right, what we could do is, oops, that should be in the exponent. I need some parentheses in here. Sorry, some formatting. Parentheses plus 3. There we go. So that just moved it to the left 3 units. So there's our horizontal shift. We can move it to the right 3 units by doing minus 3. So we can see the addition, subtraction coming through in the exponent itself is horizontal change. We could also multiply, so that's our horizontal compression by a half. This would be our horizontal stretch by 2. So again, horizontal changes are always a little opposite of how we think it should go, or it's just kind of the reverse of what vertical does. So seeing that 1/2 times x actually stretches it out by 2, but having the 2 times x shrunk it, so it compressed it by a half. So that's where we can see that notation coming through within an exponential function for the different changes that we can make with graph transformations. So let's actually graph these by hand and talk about all of the pieces that are occurring and making these changes with the transformations. So this first graph is just our y equals 2 to the x. So this is our basic function that we're working with. They give us some key points to work with, and we can clearly see our horizontal asymptote because we will want to track the horizontal asymptote. So this function here, doing the +1 on the outside of the function, this is going to be a shift up by 1. So what we can do is pick up each of those points. So where I had 0, 1, I'm going to bump that up to 0, 2. Where I had 1, 2, now I'll be 1, 3. So just moving each of those points up by 1 will give us that graph. And then it's with these vertical shifts, shifting up and down, that our asymptote will move. It won't move with the horizontal shifts, and it won't move with the stretches or compressions, but specifically with the vertical shifts, it'll move along with it. So that asymptote also moves up by 1. So with that, our graph now looks like this. Except less messy, but that's the best I can do for now. All right. For this one, we're multiplying by 3 on the outside of the function. So this is going to be a vertical stretch by 3. So where I have this vertical distance of 1 here, I'm going to triple that distance. So now I'll be up at 3. Where I have this vertical distance of 2, I would multiply that by 3, so now I'd be up at 6, which is actually off of the graph here, but I can kind of imagine it'd be like about there. And then I'm not even, this next point's way off the graph, but it'd be up at 12. Where I have a half, times 3 is 3 halves, so I'd be up at 1 1/2. At a fourth, times 3 would be 3/4, so it'd actually be about right there. And then the asymptote doesn't move at all. So the graph would look something like, gosh, I can do better than that. One more time. All right, something like that. So it's just growing a lot quicker because it's stretched out vertically. With -2 to the x, so this negative's on the outside, so this is where we reflect over the x-axis. So what we're going to do is just change all of the y values to negative. So where I have +1, it would now be -1, +2, -2, +4, -4, +1/2, -1/2, +1/4, -1/4, and the asymptote doesn't move. So we'll have something like this. All right. If the negative is, this is inside the function, since it's up in the exponent, this is where we reflect over the y-axis. So with this, we're changing our x-coordinates, negative to positive and positive to negative. So 0, 1 is going to stay put, but where I had -1, +1/2, now I'm going to have +1, +1/2. And where I had -2 1/4, now I have +2 1/4. And where I had 1, 2, now be -1, 2. And 2, 4 will now be -2, 4. So, and just connect those dots, and the asymptote didn't move at all. And now let me give you that explanation of where I said this is actually our graph of 1/2 to the x. So where that's coming through is 2 to the -x. You have this -1 here, and what we can do is evaluate that negative in that you could think of this as 2 to the -1 times x. And okay, this is kind of a big workaround, but what you could do is think of it as power to a power rule of like 2 to the -1 to the power of x. And how you can see that is our rule said power to a power, you multiply them, so -1 times x would give you that. But if you think of it in this form, 2 to the -1 is 1/2. And then we have our exponent of x. So what you could do is either graph this thinking about the transformation, or you could simplify that negative exponent and actually see that you could just be graphing 1/2 to the power of x, and it would give you the same thing. All right, one more here. We have 1 minus 2x, and if it helps, I could rearrange this as a negative 2 to the x plus 1. So I could see, okay, multiplying by negative on the outside, so that's a reflection over x. And then with the plus 1 on the outside, we're going to shift up 1 unit. So I'm going to take care of the reflection first. So I'm going to do 2 steps with this. So reflecting over the x-axis, which we've done already, would give us something like this. I'm just going to kind of get a sketch going here. And then we're going to move everything up 1 unit. Now this moving up will move our asymptote. So I'm going to pick up that horizontal asymptote and move it up 1 unit. And then I'm going to take what I graphed in green there and move all of those up 1 unit. So I'll have a point there, and that actually lands there, and here, here, here. So with that, we'll get a graph like this. Okay. So there's some basic transformations, being able to read them with this 2 to the x function. In the next video, we'll look at some more complicated transformations and kind of change this growth factor around as well.